Hello and welcome to the 15th lecture in this series. So last class we talked about interpreting vectors in Rn as derivations on C infinity functions. Let's see how this can be used to define the tangent space of a manifold. So we begin with, let me give the definition straight away, but it will not be clear in the beginning that we will get a finite dimensional vector space. So we have to do a bit more work. The tangent space to a manifold. So let M be a n manifold and let P be a point on M. We define TPM, the tangent space to M at the point P, to be the set equal to set of all derivations on C infinity M, i.e. TPM equal to set of all T, set of all linear maps from C infinity M to R satisfying the Leibniz rule at P. Note that TPM is a vector space. In other words, if T1, rather let's use a different notation for elements of TPM. So if V and W belong to TPM, then and C1, C2 are real numbers, then C1V plus C2W is also an element of TPM, i.e. C1V plus C2W is a linear map from C infinity M to R and a derivation. This is immediate from the defining property of a derivation. After all, what do we have to check? The linearity is clear enough. If you have two linear maps, then their linear combination is also a linear map. And checking that it's a derivation is not any harder. So it's just a matter of saying that C1V plus C2W, suppose I want to check it's a derivation, all I have to do is act it on a product of two functions, Fg. Then I want to know whether this is equal to C1V plus C2W this is equal to f of P times C1V plus C2W of G plus G of P C1V plus C2W of F. And the way to see it is just start with the left hand side. C1V plus C2W acting on Fg is, by definition, it is equal to C1V acting on Fg plus C2W acting on Fg. Now just use the derivation property for V and W. So I'll get C1 times F of P V of G plus G of P. Oops, so I should change it slightly. G of P, and then I have a F of V. Similarly, the second term is F of P W of G plus G of P W of F. Then I just combine the corresponding terms. So if I combine I'll combine this and this, and I'll combine this and this along with the C1 and C2. So I'll end up getting F of P times C1V of G plus C2W of G plus G of P times C1V of F plus C2W of F, which is essentially what I want here. So this is what I wanted, and that's what I have here. So it's quite straightforward to check that it is indeed a derivation. So the point is that the TPM is a vector space. However, one has to still, so what one would expect is that it's actually just again an n-dimensional vector space, since we are dealing with an n manifold, and that's the theorem. So let's state it as a theorem. That it has dimension n. Now what we have proved is that in the last lecture, we proved that Tp Rn, when the manifold is Rn itself, I didn't state it in these terms, but what I did was, in the last lecture, I showed that if you start with any derivation V on Rn with our new notation, a derivation on Rn would be an element of Tp Rn. So that's what I'm starting with. We showed if V belongs to this, actually the notation is becoming a bit inconsistent. So instead of V, let's say we showed that if X belongs to this, then X equals TV for a unique V in Rn. So this enables us to set up an isomorphism between Rn and TPRn. Hence, the map from Rn to TPRn given by V going to TV is, this map is surjective, i.e. onto. So since the previous statement says that if you start with any derivation here in the space, so an element of this space is a derivation. If I start with any derivation, it can be written as TV for some V. So that means precisely that this map here is onto. This map is onto, and not only that, it's we also seen that this map is injective. That follows from the uniqueness of this. So two different vectors cannot go to the same derivation. So because if we have seen that if TV equals TW, then V has to be equal to W. So in other words, this map is a bijection. But not only is it a bijection, this map is also linear. Also, V going to TV is linear. And this is, i.e., what does this amount to? CV1 plus CV2, C2V2. The directional derivative along this linear combination is equal to C1 TV1 plus C2 TV2. And this is again immediately clear from the definition of the directional derivative. This is not so clear from the, rather than using the definition, if we use the definition, then TVF is d by dt of f of p plus TV at t equal to 0. But if we use this, it's not immediately clear that if I put C1 V1 f of p plus t times C1 V1 plus C2 V2. This is what I would get. But then it's not immediately clear that this, I can write it as something involving, I can bring out the C1 outside, etc. Rather than use this, I would, it's easier to see if we know that this is the same thing as DFP of V. If I take this, it's immediately clear because after all, DFP is a linear map. Therefore, when I put this, then I'll just get this and one would be done. This is the same thing as C1 TV1 of F plus C2 TV2 of F. And this was TC1 V1 plus C2 V2 of F. So this equal. So using this expression here makes the linear dependence on V immediately clear. While if I use the definition, it's not immediately clear. One has to go one or two steps ahead. Now, so to summarize, we want to prove that the dimension of the space of derivations on C infinity functions on a manifold is n, and what we have proved in the last lecture is that the space of derivations on Rn, or rather on C infinity Rn, has dimension n. So how does one use this fact about Rn to get information about the whole manifold? So there's a key missing ingredient here, which I'll now talk about. Yeah, right. This is the so-called local property of derivations. But before I come to that, perhaps, even without knowing that this is dimension of TPM is the n or even finite dimensional, I can still bring in the notion of a derivative of a smooth map. So even without the theorem that dimension of TPM equal to n, we can define the derivative of a smooth map between manifolds. When we started this course, we started by defining the derivative of a smooth map between open sets in Euclidean spaces as a linear map between Rn and Rm. But now what we are going to do is we are going to replace the Rn and Rm by this notion of a tangent space. So for us, if f from m to n is smooth and p belongs to m, then dfp is going to be a map from the tangent space to m at p to the tangent space at f of p n. This is the linear map defined by so DFP the input is a vector, an element of TPM. However, an element of TPM itself is a certain linear map on a different vector space, namely C infinity functions on M. Right. So now I'm supposed to get DFP of V is supposed to be an element of this space. So in other words, it's going to be a linear map on C infinity N, which is a derivation at f of p. So it has to act on some C infinity function on n. So let's call that phi. Phi. So where here phi is, so the picture is like this. M, n, f is a map, p is a point here, f of p is a point here. Phi is a C infinity function on n. And DFP of V is going to act on that. And my definition of this is going to be just, I'll use the V. So V, let's think derivation on this side. I'm going to compose f and phi. So I'll get a C infinity function on M. Phi composed with f. So this is my definition of the derivative. And one thing is certainly clear immediately from the definition, that this association, this is linear in V. it is clear that DFP is linear. So again, what does it mean to say that this is linear? I.e., if C1, C2 belong to R, then DFP of C1 V1 plus C2 V2 is C1 DFP V1 plus, oops, so I don't need a bracket here, plus C2 DFP V2 and what in turn, I mean this is still, this is clear enough, but what this really means is that this equal to this amounts to saying that for any phi in C infinity n, the left hand side acting on this phi is equal to right hand side acting on phi. So this entire thing acting on phi should be equal to Cn df of p v1 acting on phi plus C2 df of p v2 acting on phi. At this point, everything is just a number. The left hand side is a real number, right hand side is a real number. So at this point, we just go back to this equation here, and then everything becomes immediately clear, because after all, the left hand side is C1 V1 plus C2 V2. So I would end up, instead of this V, I would end up plugging in this thing here, and so the action of C1 V1 plus C2 V2 on this function, and then just split it up and so on. So that's that. But there is one small issue in this definition, namely that I implicitly used a certain fact. So I had a smooth function phi from n to r, and f was a smooth function from m to n. I took the composition and got a function from m to r, which is this phi composed with f. But in order to act v on that, I need to know that this is still, this composition is smooth. In other words, note that we have used the following fact, which I didn't prove or even state, because I need to state it again when I talk about chain rule. So I'll return to this, but let me just mention it here. Compositions of smooth maps between manifolds are smooth. So that's this phi composed with f that I used to say that that is smooth. It's I've used this fact. But given that, it is clear that so we do have a notion of a derivative. It's defined in a very abstract but abstract way. From the way it's defined here, it's not on first sight it's not clear where derivatives are involved at all. Of course, if one remembers that v is a derivation, and we know that derivations have somehow are essentially given by derivatives, then it's clear that, and I'll be differentiating this phi as well. phi and f both. So if one recalls that, then it's clear that derivatives of phi will come into play. But that's in a somewhat vague sense. But more precisely, one would like to claim that this notion of derivative is equivalent to our earlier notion of derivative when we go back to Rn. This notion, the point is that this notion of derivative or differential of a smooth map makes sense on a manifold, while our earlier notion of derivative, of course, which involved taking ratios and norms of things and so on, so that absolutely doesn't make sense. This abstract definition makes sense, but we want to check that it coincides with the earlier definition. So I'll talk about that in the next lecture. So we'll stop here. Thank you.